Good morning students. In this session I want to discuss second unit mean value theorems, in that Taylor's and Maclaurin's theorems. Taylor's and Maclaurin's theorem contents are Taylor's and Maclaurin's theorem with reminders, alternate form of Taylor's theorem, applications of Taylor's and Maclaurin's theorems, and series expansions using Taylor's and Maclaurin's theorem. Generalized mean value theorems. The Taylor's and Maclaurin's theorems are also known as generalized mean value theorems. Taylor's theorem statement: if f from closed interval ab to R, closed interval ab is the domain of the function and real number set R is the range of the function. So function is defined as closed interval ab to R such that f dash, f double dash and so on n minus 1th derivative of f are continuous on closed interval ab, and these functions are also derivable or differentiable on open interval ab, and p is a positive integer, that is p belongs to z plus. Whenever these three conditions holds for a function f, then there exists at least one value for x, say it as c, which belongs to open interval ab such that satisfying the condition is f of b equal to f of a plus b minus a by 1 factorial f dash of a plus b minus a whole square by 2 factorial f double dash of a plus b minus a whole cube by 3 factorial f triple dash of a plus and so on plus Rn. So C belongs to open interval AB, which is satisfying this condition, where Rn is called remainder. So here the remainder, Shlomo-Milch-Roche's form of remainder, which is given by Rn equal to b minus a whole power n into b minus c whole power n minus p into f nth derivative at the point C. What is the C here? C belongs to open interval AB whole upon n minus 1 factorial into p. What is p here? P is the positive integer. So it is known as statement of Taylor's theorem. Now we can define other reminders also. To get Lagrange's form of remainder and Cauchy's form of remainder, we have to replace the value of p. Suppose putting p equal to n in this Shlomo-Milch-Roche's form of remainder, we will get Lagrange's form of remainder. Putting p equal to 1 in this Shlomo-Milch-Roche's form of remainder, we will get Cauchy's form of remainder, and the remainders are, so Lagrange's remainder, which is substituting by putting p equal to n, we will get Rn is b minus a whole power n upon n factorial into f nth derivative at the point C. Similarly, Cauchy's form of remainder, which is given by putting p equal to 1. So thus we will have Cauchy's form of remainder is b minus a whole power n into b minus c whole power n minus 1 by n minus 1 factorial into f nth derivative at C. These reminders also important. In these three reminders, the most important one is Lagrange's form of remainder. Don't forget, the Lagrange's form of remainder is given by Rn is b minus a whole power n upon n factorial into f nth derivative at the point C. Now, alternate form of Taylor's theorem, or another form of Taylor's theorem with Lagrange's form of remainder. The alternate form is f of x is a function which is defined in the closed interval a comma a plus h. But in Taylor's theorem, we will have the interval is a to b, a comma b. So here b is replaced with a plus h, and satisfying these conditions, the condition is f of x, f dash of x, f double dash of x and so on, f n minus 1th derivative at x are continuous in closed interval in closed interval a comma a plus h, and f nth derivative of x is existed in open interval a to a plus h, then there exists at least one value, real value theta, which lies between 0 and 1, and satisfying the equation f of a plus h is f of a plus h into f dash of a plus h square by 2 factorial f double dash of a plus and so on plus h power n minus 1 by n minus 1 factorial f n minus 1th derivative at a plus h power n by n factorial f nth derivative at the point a plus theta h. What is theta here? Theta is the value which lies between 0 and 1, open interval 0 and 1. This remainder Rn is called Lagrange's form of remainder. The Lagrange's form of remainder is given by Rn equal to h power n by n factorial f nth derivative of a plus theta h. It is called Lagrange's form of remainder. Now, the alternative form from a plus h is b is replaced, then we will get the above formula becomes f of b equal to f of a plus b minus a by 1 factorial into f dash of a plus b minus a whole square by 2 factorial f double dash of a plus and so on plus b minus a whole power n by n factorial f nth derivative at the point c, where c lies between a to b. So clearly a plus h is replaced with b, so that we will get the first formula, that is the Taylor's theorem formula for f of x, which is defined in the interval closed interval a comma b. Now the Maclaurin's theorem with Lagrange's form of remainder, so which is obtained by replacing a as 0 and h as x in this equation we will get the Maclaurin's theorem formula, that is f of x is f of 0 plus x by 1 factorial f dash of 0 plus x square by 2 factorial f double dash of 0 plus and so on plus x power n by n factorial f nth derivative at theta x. This is called Lagrange's form of remainder, and the statement is known as Maclaurin's theorem. So this is Lagrange's form of remainder. What is theta here? Theta is the real number which lies between 0 to 1, open interval 0 comma 1. So it is the alternate form of Maclaurin's theorem. Now Maclaurin's theorem statement is, if f from closed interval 0 comma x to r such that satisfying the three conditions, the three conditions are f, f dash, f double dash and so on, n minus 1th derivative of f are continuous in closed interval 0 comma x. So here the interval for Maclaurin's theorem is closed interval 0 comma x, but in Taylor's theorem the interval is a comma b. So here we have to use 0 comma x. The initial value is 0, ending value is some x, and these functions are derivable or differentiable in open interval 0 comma x, and p is a positive integer. Whenever these three conditions holds for a function f, then there exists a point theta which lies between open interval 0 comma x and satisfying the condition. The condition is f of x is f of 0 plus x by 1 factorial f dash of 0 plus x square by 2 factorial f double dash of 0 plus and so on plus x power n by n factorial f nth derivative at theta x, where Rn is called Lagrange's form of remainder. Here also we have three forms for reminders, that is Maclaurins form of remainder, Lagrange's form of remainder and Cauchy's form of remainder. The reminders are Maclaurins form of remainder is Rn is x power n into 1 minus theta whole to the power of n minus p into f nth derivative at the point theta x whole upon n minus 1 factorial into p. is called Shlomo-Milch-Roche's form of remainder. Now to get Lagrange's form of remainder, we have to put p equal to n in this formula, so that we will get x power n by n factorial, because n minus 1 factorial into n is n factorial into f nth derivative at the point theta x. It is called Lagrange's form of remainder. Now to get Cauchy's form of remainder, here we have to put p equal to 1. So substituting p equal to 1, we will get Rn is x power n into 1 minus theta whole to the power of n minus 1 by n minus 1 factorial into 1, that is n minus 1 factorial. F nth derivative at the point theta x is called Cauchy's form of remainder. So don't forget, in all these the Lagrange's form of remainder is important one, that is Rn is x power n by n factorial f nth derivative at theta x. Now applications of Taylor's and Maclaurin's theorem. The application is, the problem is, verify Taylor's theorem for the function f of x, which is defined as 1 minus x whole to the power of 5 by 2 with Lagrange's form of remainder up to 2 terms in the interval closed interval 0, 1. So given f of x and f dash of x are continuous in closed interval 0, 1, while f double dash of x is differentiable in open interval 0, 1. So what is n here? N value is 2, up to 2 terms. That may be f double dash of x must and should be differentiable in open interval 0, 1. So thus f of x satisfies all the conditions of Taylor's theorem. And we can define the p as 2. What is p here? Positive integer. P can be defined as p equal to 2. In Taylor's theorem, with Lagrange's form of remainder up to 2 terms, n is the number of terms in the remainder, that is 2, and which is equal to p. Since we are using Lagrange's form of remainder, what is the condition of Lagrange's form of remainder? So to get Lagrange's form of remainder, we have to take p equal to n. So that is n is here 2, that is p equal to 2, and a is 0 and x is 1. Since the given interval is a closed interval 0, 1. So thus we will have a formula, that is f of x is f of 0 plus x by 1 factorial f dash of 0 plus x square by 2 factorial f double dash of theta x, where theta lies between open interval 0, 1. So we have to use Lagrange's form of remainder up to how many terms? 2 terms. After 2 terms, we have to use Lagrange's form of remainder. What is the Lagrange's form of remainder? X power n by n factorial f nth derivative at theta x. But n is 2 here, so that we have to use x square by 2 factorial f double dash of theta x. Now we have to substitute the required values, that is f of 0, f dash of 0 and f double dash of theta x. So f dash of x is obtained just by taking the differentiation for f of x, the derivative of f of x with respect to x, which will respectively gives the f dash of x. So the derivative is given by 5 by 2 into 1 minus x whole power 5 by 2 minus 1, that is 3 by 2, and the derivative of 1 minus x, 1 derivative is 0, minus x derivative is minus 1. So thus we will have minus 5 by 2 into 1 minus x whole to the power of 3 by 2. So we have to know about the formula. The derivative of x power n is n into x power n minus 1. The derivative of a plus bx whole power n is n into a plus bx whole power n minus 1 into b. So that again differentiating f dash of x with respect to x, we will get f double dash of x. So these are the successive derivatives of f of x with respect to x, f dash of x and f double dash of x. Now substituting the functional values, that is f of 0, f dash of 0, f dash of 0 is obtained by replacing x equal to 0 in f dash of x, f double dash of theta h, which is obtained by replacing x equal to theta h in f double dash of x. So f double dash of theta h is f double dash of theta, h is here 1, thus we will have 15 by 4 into 1 minus theta whole to the power of 1 by 2. Now substituting all these values and simplifying for theta, thus we will have a value of our theta. The theta value is 9 by 25, that is approximately 0.36, clearly which lies between 0 and 1, thus verifying the Taylor's theorem. Another application, verify the Taylor's theorem for the function f of x is x into x minus 1 into x minus 2 in the interval closed interval 0 comma 1 by 2 with the Lagrange's form of remainder up to 2 terms. The Taylor's theorem, we have to take the remainder up to 2 terms. So what is the statement here? F of b is f of a first term, b minus a by 1 factorial f dash of a second term, and now we have to take remainder term which is given by b minus a whole power n by n factorial into f nth derivative at c. But what is n here? N is 2, so that we have to use b minus a whole square by 2 factorial f double dash of c, but c lies between a to b. So here the continuous function f is and derivable also, thus we will have f dash of x is continuous on closed interval ab and f double dash of x is existed in open interval ab. So all the conditions of Taylor's theorem are clearly satisfied. So f of x in simple form we will have cubic polynomial expression, that is x cube negative 3x square plus positive 2x. The result 1 is valid for this polynomial in closed interval 0 comma 1 by 2. Now obtaining the values or substituting the values, a as 0, b as 1 by 2. Now f dash of x is obtained by taking the derivative for f dash of x, and f double dash of c is obtained by taking the derivative for f double dash of x. That means f of x is differentiated twice. So once we have to differentiate, we will get 3x square minus 6x plus 2, and again differentiating we will get 6x minus 6. Now replacing x as c, we will get f double dash of c is 6c minus 6. Now substituting all these values in this equation and obtaining for c value, so on simplifying we will get c value as 1 by 6. Clearly this c value is lies in the open interval 0 comma 1 by 2. Hence this shows that the Taylor's theorem is clearly verified because the value of c is existed in open interval 0 comma 1 by 2. The Taylor's theorem is clearly verified. Now verify Maclaurins theorem for the function f of x 1 minus x whole to the power of 5 by 2 with Lagrange's form of remainder up to 3 terms when x is 1. So now we have to expand Maclaurin's theorem up to 3 terms. The formula is f of x is f of 0 first term, x by 1 factorial f dash of 0 second term, x squared by 2 factorial f double dash of 0 third term. After these 3 terms we have to write the remainder term. The remainder term is x power n by n factorial f nth derivative at theta h. But what is n here? 3, because the number of terms are 3 here, that is x cube by 3 factorial f triple dash of theta h. Now substituting the above values, that means f of x which is differentiated f dash of x, again differentiating we will get f double dash of x, again differentiating we will get f triple dash of x, and the functional values at the point 0, f of 0, 1, f dash of 0, negative 5 by 2, f double dash of 0, 15 by 4, f triple dash of theta h. So f triple dash of theta h is f triple dash of theta, that is negative 15 by 8, 1 minus theta whole power minus 1 by 2. Now substituting all these values and computing theta value, theta is 9 by 36, clearly belongs to open interval 0 comma 1. Hence the Maclaurin's theorem is clearly verified. Now calculate the approximate value of root 10 to 4 decimal places using Taylor's theorem. So we have f of x plus h, which is defined as square root of x plus 1. But what is x here? X is to be taken as 9. 9 plus 1 is 10. So root of x plus 1 is root 10. Now we have to calculate root 10 here. For this we have to define f of x plus h as root 10. Now x can be taken as the nearest root. What is the nearest root? Well known root is root 9. What is the value of root 9? 3. So that we have to take x as 9 here, and h is the small increment in x, that is h value is 1 here. So x is 9 and h is 1. So that f of x plus h is defined as square root of 10. Now f of x is root x. So f of 9 is root 9. Root 9 value is 3. F dash of x is the derivative of f of x with respect to x. X power 1 by 2 derivative, that is 1 by 2 into x power 1 by 2 minus 1 x power minus 1 by 2, which implies that f dash of 9, the functional value at the point 9 is 1 by 6, that is 9 power minus 1 by 2, but 9 power minus 1 by 2, 9 can be written as 3 square whole power minus 1 by 2, 2 get cancelled, 3 power minus 1, but 3 power minus 1 is 1 by 3, already we have 1 by 2, half into 1 by 3 is 1 by 6. So this is the value of f dash of 9. And f double dash of x, which is obtained by again differentiating f dash of x with respect to x. Half is the constant, x power minus 1 by 2 derivative is minus 1 by 2 into x to the power of minus 3 by 2. Half into minus 1 by 2 is minus 1 by 4. Now f double dash of 9, which is obtained by replacing x as 9. So we will get minus 1 by 4 into 27. So same thing, just we have to differentiate the function double dash of x with respect to x again and obtaining the value at the point 9. These are the functions and these are the functional values at 9. Now we will have a Taylor's series expansion. What is the expansion? F of x plus h is f of x plus h into f dash of x plus h square by 2 factorial f double dash of x plus and so on, which is obtained by just by removing the remainder term in Maclaurin's theorem. In Maclaurin's theorem, just we have to remove the remainder term. So we will get, substituting all the above values, we will get the root 10 value. Thank you. For any doubts or clarifications, please contact. In next class, we will see the problems related to Taylor's and Maclaurin's series expansions. Next class is about for Taylor's and Maclaurin's series expansions.